All right, now let us start. Okay, so potentiometer is our last subtopic in chapter 3. So there are four cases that we're going to look at right now. Okay, the four cases, it covers three different applications. The first one is to measure the unknown EMF. So unknown EMF, I show you two resistance. One is just an unknown EMF. One is an unknown EMF, but now you added external resistance in the upper loop. So this is the external resistance. All right, and then we have a case where we compare two EMF. That is a second application. And then the last case is to measure the internal resistance of a cell. So three applications, and you need to know all three of them because the questions might ask you to state it, or it might come out as a objective questions. So if you look at the first diagram to measure unknown EMF, now if you notice, I've already highlighted the upper loop. So it doesn't matter which applications you are looking at, the main focus, the first things that you need to look at is the upper loop. What happened in this blue color loop? How many components do we have in this blue color loop? If just the battery, the EMF itself, and the potentiometer, now potentiometer is the AB line, okay, the line AB, this is a potentiometer. So if you just have the EMF and the potentiometer itself, then straight away what we can say is that EMF equals to VAB. Okay, EMF equals to VAB. And then, okay, and then if, okay, now if it's being connected to an additional unknown voltage, which is EMF X, so what is going to happen? Now you have a galvanometer and you have a jockey. Okay, so remember that I showed you yesterday, jockey is a pen-looking thing. So you just slide it along the potentiometer AB to identify where is the balance point. So for example, here it shows you point C is the balance point. When it reaches balance point, it means that galvanometer reading is equal to 0 ampere. Okay, no deflection. So galvanometer, okay, the screen is like this. Remember? So the 0 is located at the center. So you have a 1 on both sides, 2 on both sides. So it's being deflected, then that means there's a current flowing through it. And the directions of deflection, it tells us the directions of the current flow. Okay, whether the current is flowing in the clockwise directions or anti-clockwise direction. It all depends on the galvanometer. So galvanometer will tell us not just that there's a current flow in the circuit, but it also shows us the direction of the current flow. So in some case, the deflection, it will just point towards one direction. Okay, if it points toward one direction, what does it mean? Okay, there are two possibilities. The first one is that now you connect your unknown EMF in the wrong diagram, in a wrong position. Okay, wrong direction. When you have EMF, the upper loop, where the positive terminal is on the left-hand side, negative terminal is on the right-hand side, then when it comes to this unknown EMF, it also must follow this direction. Okay, where you have a positive terminal on the left-hand side and negative terminal on the right-hand side. The diagram is like this. All right. If you put it in the wrong direction, then what is going to happen? Your galvanometer will be deflected towards just one direction. Okay, it won't change direction. It will never achieve balance point. And another possibility is that when your unknown voltage is larger than your source voltage, okay, your EMF here. If EMF X is larger than EMF, then once again, this galvanometer will never be equal to 0, and it will always reflect one direction. Okay, to which directions? To the direction that follows the current flow in the lower loop. Okay, now when it comes to potentiometer, we have two current. First current is coming from the upper loop. Okay, the blue color current here. It is coming from the upper loop. And then the second current will be coming from the lower loop. Okay, this lower loop, it will give you another current. So what is going to happen? When they reach point A, they are actually going to combine and enter A as a new current, all right, as a total current. Now, when you keep increasing the voltage across AC, okay, what is going to happen is that when they achieve balance point, now what you can do, you can imagine AC as an imaginary battery here. Okay, just assumption. So there is an imaginary battery here. So when AC is equals to EMF X, okay, when BAC is equals to EMF X, then there's no potential difference between AC and EMF X anymore. If no potential difference, then this current, it won't flow anymore. Okay, this current will stop flowing, meaning that no current flow in this lower loop. Then what happens in upper loop? Now in upper loop, your EMF is still larger than VAC. So there's still a potential difference. Okay, so it will just keep flowing. It will just keep flowing. All right, so it won't affect your upper loop. But what is happening when it reach balance? Okay, when it reach balance point, the current will stop to flow. Okay, the current will stop flowing in the lower loop. So that is what happens right here. All right, it has enough energy to stop current from flowing from the lower loop. So for the upper loop, it doesn't matter because there's a still potential difference. As long as there is a potential difference, because AB is actually just a resistor. Okay, it's just a resistor. But to make it easier for you to imagine, when it comes to lower loop, you can treat it as an imaginary voltage. Okay, and as an imaginary voltage. So what happens right here is I and IX, now they're facing each other with the same terminal. So when VAC is large enough, this IX will be stopped from flowing into junction A. So it won't flow. Okay, it won't flow. So what is going to happen is that the current will just keep flowing in the upper loop with current I. Okay, with current I. So that is what happens in our circuit. And then when it comes to potentiometer questions, remember you always treat it as you always use potential divider concept to solve it. Okay, so potential divider is happening along this AB again. So this AB actually plays a very important role in a potentiometer questions. Okay, so when it comes to potential divider, remember the concept in potential divider for the first diagram, it tells us that VAC over RAC, this is actually equals to the current, the equation for current. Okay, but now since it's in the potential divider, it is also equals to VAC, V over R at all the other component. So if you look at this upper loop, if you apply potential divider concept, you can actually treat this AC as RAC. Okay, as RAC. And then here you actually has another resistor. Okay, RCB. All right, that is what is happening right here. Okay, that is what happening right here. So we can treat it, we can assume, we can imagine there's a two imaginary resistor right here. So other than VAC, it is also equals to VBC over CB. Okay, the subscript CB. I'm going to follow the sequence here. VCB over RCB. Okay, RCB. So RCB and VCB, now we are done. Now, other than this, well, if you don't want to treat it as two separate resistors, what you can do is you can treat this whole AB as one resistor. Okay, the whole potentiometer as one resistor known as RAB. So meaning that it can be also equals to VAB over RAB. Okay, VAB over RAB. So this is the key idea in solving potentiometer questions. But then, if you recall, okay, the things that we have seen here, okay, the things that we have seen in a potential divider, other than R, okay, this AB is actually a wire. We are talking about the length. Okay, we're talking about the length. So we have LAC and also LAB right here. How are we going to link these equations to the length? Now let us focus on, now since we want to measure the unknown EMF, let us focus on what happens in AC, okay, and also AB. CB is not very useful in potentiometer question, so we can ignore it first. So what we can do from this relationship, we just take out the two components that we want. Okay, the two parts that plays an important role in potentiometer. So VAC over RAC is equals to VAB over RAB. If you rearrange the equation, you will obtain VAC over VAB equals to RAC over RAB, right? in which it makes sense. Why? Because what we do know is that V is equals to IR. In a series circuit, V is proportional to R. That is the things that we know. And then from the equations, okay, from the equations, R equals to rho L over A. Since you are looking at the same wire, so rho and A, they are constant. Okay, they are constant. So meanings that, R is proportional to L. When R is directly proportional to L, these equations can then be written as, okay, these equations can then be written as RAC over RAB. It's also equals to LAC over LAB. Since you're looking at just the ratio between two lengths, if they are directly proportional, then it can be written as this. Okay, it can be replacing as a L over L. So if you're unsure, you can actually substitute R equals to rho L over A into RAC, R equals to rho L over A into RAB, and then you cancel out the constant value. Eventually, you obtain the same ratio. Okay, so untuk ratio, untuk R over R, L over L, kalau hubungan directly proportional, Anda boleh tulis begini, tak ada masalah. Okay, Anda boleh terus tukar R menjadi L, R menjadi L. Sebab apa? Sebab directly proportional. Okay, untuk directly proportional punya relationship, kalau Anda pasti yang lain punya adalah constant, actually you can just rewrite the equations like this. Tak payah buat derivations untuk tunjuk. Okay, because of proportional, if R is proportional to L, then RAC over RAV is definitely equals to LAC over LAB because directly proportional. Kalau bukan directly proportional, let's say, okay, contoh. Let's say if R is proportional to L square, then you cannot say RAC over RAB equals to LAC over LAB anymore. It will become RAC over RAB equals to LAC square over LAB square. Okay, dia terpulang pada proportional. Okay, dia terpulang pada relationship. So that's why if you look at the short notes that I give you here, okay, applying the concept of potential divider, therefore we obtain these two set of equation. Okay, these two set of equation. So basically, you can just write them as a one long equation. RAC over RAB equals to VAC over VAB equals to LAC over LAB. And then what is the next step? After you know these two concepts, okay, after you understand these two concepts, basically you can sub this EMF equals to VAV into the equations right here, and then EMF X equals to VAC into the equations here. Okay, or you can determine VAC by using this equation, depending on whether you are given L or you are given R. Usually it will be given L and R, and it asks you to determine VAC. So once you have VAC, then you know that is your EMF X. So that is the idea. That is a very simple, okay, very simple ways of solving it. So the first thing that you need is the relationship from the upper loop. Now let's look at the second case. In this upper loop, the blue color loop, okay, I'm going to call this upper loop. Okay, I like to call it upper loop because we have several loop in potentiometer question. So in this upper loop, usually you can get one equation from it. Okay, for instance, this one now it comes with an external resistance. Therefore, you have EMF minus VR. Okay, this is actually your VR. This part is actually VR. So EMF minus VR equals to VAB because when you add up the V in the whole circuit, it is equals to EMF. If you don't trust me, you can apply Kirchhoff law to solve it. Okay, kamu boleh je pakai Kirchhoff law untuk satu loop ini, tak ada masalah juga. Okay, you can use Kirchhoff law in any circuit questions as long as there's a loop. Okay, your Kirchhoff law. So EMF minus VAV minus VR equals to 0. Rearrange, you obtain EMF minus VR equals to VAB. Okay, so this is the first relationship that we obtain from the upper loop. The first equations that we obtain from the upper loop. For the lower loop, well, since you just have the EMF X, straight away is equals to VAC if it is balanced once again. So jockey and this galvanometer is very important. You need to confirm, you need to ensure that they are balanced before you solve it. So if you apply a concept of potential divider and potentiometer, once again, you're just going to get the same equation. Okay, because potential divider is just happening along this horizontal line. And for every single questions in the potentiometer, this horizontal line you will just have this exactly the same equation, the same relationship, because that is what happens in potential divider. All right, you're just playing with the ratio. Okay, you're just playing with the ratio along this line. So applying the concept of potential divider, it can be used in any application. The only things that you need to be careful is this one, applying the concept of parallel combination. Right? So we are just going to determine the idea. If you have a look like this, okay, which part is parallel to this potentiometer, which is your EMF minus VR, this whole thing, this blue color path, it is parallel to this AB. And then when it comes to the lower loop, EMFN is parallel to AC. So basically you have two parallel circuits right here. Okay, the blue color path parallel to AB. The lower loop, the one without color, is parallel to AC. So you have two parallel circuit, two parallel concept right here. All right. So potentiometer actually is not very complicated. It's just combine the parallel circuit concept and also potential divider concept in the same question. So compared to EMF, once again, the idea is exactly the same. Okay, when you have a this relationship, now it just want to compare two EMF, meaning that you don't have to look at what happens along this potentiometer. You just want to see what happens along AC and AD. Okay, AC and AD. Now, once again, remember the key concept, the key idea is when your galvanometer is balanced, then it won't affect the current flow in the upper loop. The current flow in the upper loop, it doesn't matter whether your jockey is touching point C or point D, they will give you the same I. So same I means that you will have a same VAC over RAC. You will have a same VAD over RAD because you have a same current flowing in the upper circuit. So if you want to compare the two EMF, okay, rearranging the equations, you will see that VAC over VAD is equals to RAC over RAD, and it is also equals to LAC over LAD. Okay, where your VAC is equals to your EMF1 and your VAD is equals to your EMF2, your unknown EMF. Okay, so we are playing with, once again, the parallel circuit idea and also the ratio, okay, the potential divider idea. Okay, from potential divider, we obtain this set of relationship, and then from here, we then determine the values of EMF1 and EMF2. We can then determine the relationship. We can then compare between the values of EMF1 and EMF2. Now let's look at the last one. This one we already discussed it yesterday, right? When we go through the lab manual, when we go through the pre-lab. So I'm going to explain it once again quickly. But now this one, you have two loops. Okay, this is your upper loop. Okay, this is your upper loop. Two very obvious loops. And it is not just for you. Okay, I introduced this idea to you. It's not just for you to solve the questions involve internal resistance, but also to try to solve the questions with two loops, even if the question didn't ask you to determine the internal resistance. Okay, kadang-kadang soalan tak bagi kamu internal resistance, tak minta Anda tentukan internal resistance. Apa yang dia minta? Dia minta Anda selesaikan, mungkin cari external R. Then you need to know the idea. So in this question, okay, I have two loops. One upper loop and one lower loop. Okay, one upper loop and one lower loop. This is my lower loop. Okay, this is my lower loop. So what am I going to do right now? As usual, I want to form an equation for upper loop. I want to form an equation for lower loop. Okay, I want to form an equation for upper loop. I want to form an equation for lower loop. In my upper loop, okay, in my upper loop, EMF is still equals to VAB. Okay, this is from the upper loop. All right, this is from the upper loop. And now when it comes to lower loop, okay, when it comes to lower loop, so when you have this type of questions, you need to look at two different things though. One is with S open, one is with S closed. All right, so we'll look at that one in a bit. So when it comes to lower loop, if you close the switch S, okay, with switch S closed, what is going to happen? You have an equations with EMF1 equals to IR plus R. Okay, you have two equations. Okay, you have two equations. And this one, it exists when you close the loop. Okay, close S. If S is open, okay, if S is open, then you will have EMF1 equals to VAC if S open. Okay, if S open. So once you know these two relationship, okay, these two equations, you can then go back to playing with the potential divider concept again. Right? So you have VAC and VAB right here, this potentiometer. Once again, the relationship that we have right here, okay, once again, we want to look at what happens when S open and S close. All right, when S open, okay, when S open, when this one open, you're actually disconnecting the lower circuit from the, okay, you're actually disconnecting this part. Oops, should be this. Okay, you're actually disconnecting this external resistor from my battery. Okay, so the lower loop right now, it has just the battery. So if S open, no current flowing in the lower loop. Okay, no current flowing in the lower loop. So the things that we have is EMF equals to VAB. This is always true because in upper loop, we have just this blue color loop, no other external resistance. And then in the lower loop with S open, EMF1 equals to VAC. And then we can say, okay, we can say what happens along here is that VAC over VAB equals to RAC over RAB equals to LAC over LAB. Now, what happens if I close a switch? If I close a switch, meaning that I have a complete loop right here. Okay, I'm forming a complete loop right now. So if I have a complete loop here, it means that the current will start to flow. Okay, they will have their own current. So this is another part that you have to be careful. Here you have a current I, a blue color current. When lower loop, it has its own complete circuit, then it will have its own current flowing through it. This I1 has nothing to do with I. Okay, it has nothing to do with I. When your galvanometer is balanced. So when S open, when S closed, when S closed, again, in this upper loop, we have EMF equals to VAB. But now in this lower loop, we have EMF1 equals to V across external resistor, VR, okay, plus V terminal, okay, V terminal. So if you rearrange these equations, okay, if you rearrange these equations, VR is then equals to EMF1 minus VR. Why? The reason I rearrange it like this, that is because when it comes to this case, when you close switch S, now the part that is parallel to AC is no longer the EMF1, but it is the terminal voltage. Okay, your terminal voltage, I'm going to call this point M, point N. So VR is actually equals to your VMN. Okay, VMN. So your terminal voltage. This terminal voltage is now equals to VAC. But of course, this VAC is no longer equals to VAC when S open. It is now known as VAC prime. Okay, VAC prime over VAB equals to RAC prime over RAB equals to LAC prime over LAB. Okay, LAC prime over LAB. So what you can say in these two diagrams, in these two cases, is that when S open, okay, VAB is equals to VAC. When S is closed, VAB is equals to EMF, but now your VAC is no longer equals to EMF1, but it is equals to your VMN. So your VMN at the same time, it's also equals to VAC prime. Okay, VAC prime. So from here, you just see what is the information given. From there, you try to solve the question. Okay, so it's quite hard to explain how to apply it to you without looking at any example. So this is just the concept. Okay, this is just the concept. It shows you what happened with and without switch as open. All right. So I give you a few minutes to write it down first, all this summary. Okay, all this summary before I proceed to example 16, how to solve questions with internal resistance. Okay, kita akan apply juga macam mana kita nak solve questions with internal resistance. But for now, I give you some time to write it down. So now let us try one question. Biar kita cuba satu soalan, tengok macam mana nak jawab dia. A potentiometer consists of a uniform wire of length. Okay, so initially, okay, now we want to focus on what happens along this wire. So initially, your LXY is equals to 100 cm. And resistance, the total resistance across the wire, your RXY is equals to 5 ohm. And they're connected in series with a 2 ohm. Now you have an external resistor. Okay, and the driver cell, 3 volt, this is your EMF, with an internal resistance. Remember, whenever you have internal resistance in your calculation, you just treat it like all the other external resistance. Okay, so when a potentiometer is used to measure the unknown EMF, EMF1, the balance length. Okay, so balance, the key words is now the balance length is equals to 75 cm. When it is balanced, the information that we have is EMF1 equals to Vxj. Okay, when it is balanced. And the information that we have right now in the diagram, what we have Vxj here, we have Vjy here, okay, and then we have Vxy, of course. We are looking at what happens across this wire. So now let us begin with the ratio. So I equals to Vxj over, okay, now instead of Rxj, let me see what can I do. Okay, well, I'm going to stick to Rxj first, and then it is equals to Vxy over Rxy, all right? And remember, other than that, okay, we can also transform the equations into Vxj over Lxj equals to Vxy over Lxy, okay? And then there's one more equation that we can use, but that one I'll leave it first. Okay, I'll leave it first. Now let's see how are we going to solve this equation. We want to determine Vxj. Okay, we want to determine Vxj. So we are going to need the values of the, what do we need? Now we do have the length. We have Lxj, and then what else do we have? We have a Lxy. Meaning that the equations that we're going to use is actually this equation. Okay, kita nak guna equations in his papa because we are given Lxj, we are given Lxy. And then we want to determine Vxj. So the remaining thing is we're going to see, do we have Vxy? Can we obtain an equation for Vxy? Of course you can. Now let us focus on what happens in the upper loop. Okay, what happens in the upper loop? So in the upper loop, you can actually form an equation by using Kirchhoff's second law. All right, you can actually form an equation by using Kirchhoff's second law, which is, okay, let me begin here. So first, okay, I'm going to choose a loop first. So when it passes through my first resistor right here, it experiences a potential drop. So negative IR minus IR. Okay, now it flows from a negative terminal to positive terminal plus EMF minus Vxy. Okay, across this one equals to 0. So Vxy is actually equals to what? Vxy is equals to EMF minus IR minus IR. Now you do have all of these informations, right? Which is then equals to EMF, which is equals to 3 volt. Okay, 3 volt minus, do I have the I? Let me see. Well, seems like I don't have the current, but I can determine the current if I expand this equation. Okay, if I expand this equation into IRX. So now what I have, if you look at the equation, I have IRX equals to 3 minus IR minus IR. Okay, saya nak tentukan nilai dia dulu. Okay, saya nak tentukan nilai I dulu. Because if I don't have I, then I cannot solve the question. Right? So from here, I then have Rx given is, Rx, do I have the values of Rx? Yes. The wire, the line is 5. Okay, the reading is 5. And then equals to 3 minus I2 minus I2. Rearrange the equation, I is equals to 0.333 ampere. Okay, so once you have I, you can then determine Vxy. So Vxy is equals to IRxy. Okay, which is then equals to 0.333 times 5. Therefore, Rxy times 0.333 will give you, okay, will give you Vxy equals to 1.67 volt. You can then apply these equations to determine Vxj. So Vxj is equals to Lxj 75 cm over 100 cm times 1.67, which is then equals to 1.24 volt. Okay, which tells you since EMF1 equals to Vxj, it is then equals to 1.24 volt. So that is how you solve it. You see, basically it combined the idea of potential divider and also Kirchhoff law in one question. Okay, dia gabungkan potential divider dengan Kirchhoff law punya idea di dalam satu soalan. Alright, so okay, you can write it down. Example 16, the last example in chapter 3. In the circuit shown, the EMF of the driver cell, EMF1 equals to 2 volt, and its internal resistance is negligible. So this EMF1, it has a 0 internal resistance. And the length of the slide wire AB is 100 cm. So LAB, okay, given LAB is equals to 100 cm, EMF1 equals to 2 volt, information is given. When switch S open, okay, when switch S is open, the balance length AJ is 75 cm. And when switch S is closed, the balance length is now 65 cm. So you're given two different statements. Okay, so one is your LAJ. Okay, your LAJ is 75. Oops. Okay, LAJ is 75. LAJ prime. Okay, saya panggil dia LAJ prime is 65 cm. So biasanya, usually we use prime to show that there's a difference between LAJ prime with the original value. Okay, to represent this is the second case. Okay, second case. So calculate the EMF of the cell. Now, when it comes to calculating EMF, okay, determining EMF, usually, okay, or most of the time, we don't want current flow in the lower circuit. Okay, so if question asks you to calculate EMF, so the first thing that you have to know, we don't want current flow. Okay, don't want current flow in lower loop. So if you don't want current flow in the lower loop, what does it mean? Then you open the switch. Okay, so switch is open. So that is how we analyze. That is how we determine whether we want to use the information in the yellow color or we want to use the information in the green color. All right. So once again, this is my upper loop. Okay, I'm going to label it so that you understand what am I talking about. So this is the lower loop. Okay, upper loop, lower loop. So we don't want current flow in the lower loop. Therefore, we open the switch S. All right, so if S is open, what is the information that we have? Remember, when it comes to upper loop, it doesn't matter whether switch S is open or is closed. The only important information about this upper loop is when your galvanometer reading is balanced. When your galvanometer is balanced, when the jockey is located at the balance point. So when S is open, when switch S is open, EMF1 is always equals to VAB. And straight away, because S is open, meaning that you are ignoring this lower loop, what you are looking at is this horizontal line only. Okay, it's this horizontal line. No current flow, no internal resistance. So this line, okay, this 2 point, it is parallel to point AJ. So if it is parallel to point AJ, we can say that EMF2 is equals to VAJ. Okay, VAJ. And if you look at the informations given is the length, LACN, LAJ equals to 75. Meaning that in order to solve this question, we are going to use relationship VAB over VAJ equals to LAB over LAJ to solve it. Okay, why? Because VAB, we have EMF1, VAJ, we have EMF2. So EMF1 over EMF2 is equals to LAB over LAJ. Plug in the value, this one, and also this one. You will then obtain EMF2 equals to 1.5 volt. So that is how you solve this type of question. Your first step is to determine the values of EMF2 first, before you determine the internal resistance. Okay, you need EMF2 before determining the values of internal resistance. All right. So now let's look at this one, B. Okay, B, it's asking for internal resistance. So when you talk about internal resistance of EMF2, means that now it has current flow. Okay, it has current flowing through EMF, okay, EMF2. Meaning that when it comes to questions B, switch is closed. Okay, switch is closed. All right, so if switch is closed, then we will have another different story. Okay, so in the upper loop, again, we have EMF1 equals to VAB. But now in the lower loop, it is no longer EMF equals to VAJ. Now you have to take into consideration the whole loop. Okay, the whole loop with internal resistance located at here. This is your R. So in this case, what we have right now is we have EMF2 minus VR equals to VR. Okay, this VR is actually our terminal voltage. And at this point, my terminal voltage, okay, let's say this is my VMN. My VMN, it's equals to VR because I have just one resistor. If you have more than one, of course, you need to find the resultant resistance, all right? If you have more than one. All right, so this is then equals to VAJ prime, okay? VAJ prime, because now you have a new length, okay? You have a new length. So once you have these equations, what are you going to do? Basically, you just apply the same equation, but rather than VAJ, now I use VAB over VAJ prime equals to LAB over LAJ prime. VAB again is 2 LAJ. Now what I have right here, now I don't have the I yet. I don't have VR, right? So I need to determine the values of VR first if I want to apply this equation, because EMF2 minus VR is equal to VAJ. So I'm missing some of the information right here. So let me determine the value first. Okay, let me determine the values of the current. So, okay, what am I going to do? I have EMF2 minus VR equals to VR. Okay, equals to VR. So given, yeah, let me see. So given I have what value? Now I have this 4 ohm. Okay, I have 4 ohms right here. And then my VAJ, do I have any information about VAJ? Okay, meaning that I can determine VAJ first. Then I plug it here. Okay, so I reverse the process. So VAB over VAJ equals to LAB over LAJ. VAB is 2 over VAJ prime. We don't have the value yet. It is then equals to LAB. AB given is 100 cm. LAJ prime given is 65 cm. From here, we are able to determine VAJ prime is equals to 1.3 volt. Okay, VAJ prime equals to 1.3 volt. All right, so from here, from VAJ prime, we can then determine the values of I. Okay, we can then determine the values of I by using VAJ prime equals to VR, which is equals to VIR. So 1.3 equals to I times the R, which is 4. I is equals to 0.615 ampere. So from here, we then apply this equation. Okay, we then apply these equations. So VAJ prime, other than equals to IR, it is also equals to EMF2 minus IR. Okay, EMF2 minus IR. So, okay, so what I have right now, VAJ prime is 1.3 equals to EMF2 is coming from previous question. Okay, it's coming from previous question because EMF is a constant value as long as you're still using the same battery. So 1.5 minus 0.615 R. So R is then equals to 0. Oh, not 0.615. Sorry, I got a mistake right here. It should be 0.3. 0.325. Okay, 0.325. So R is equals to 0.615 ohm. Okay, ohm. So that is how you solve it. Okay, that is how you solve it. The key idea is always the same. You're playing with where is the parallel circuit, and then you're playing with the potential divider relationship. Okay, potential divider relationship. So sometimes the questions might not ask you to determine the internal resistance. Sometimes you might have a questions like here. Okay, so this is the example that I wanted to do after this. But before that, I give you few minutes to write down this one. Okay, kamu tulis dia punya solution dengan kemas, dengan sebab. Okay, why? Okay, when to use switch open, when to use switch is closed. Okay, so dia ada syarat-syarat dia. So bagi anda beberapa minit untuk catat before I give you some time to write down the additional question. Okay, the extra question. Okay, so this is the last questions in chapter 3, but I want you to write down this additional question. Okay, I give you this one additional questions. It's different than the example 16, okay, but it uses the same concept, the concept of upper loop and lower loop. Okay, so I wanted to try it, and the answer, wait, yeah, let me see what is the answer. The answer should be, if you got it right, the answer should be 85.7 cm. All right, so this one I give it as your homework, okay, as your homework.